University. Okay. Please shortly introduce your name and yourself. From here.
Good morning, everyone. We're H105 from National Experimental High School in Hsinchu Science Park, and these are my examples.
Yes.
Good morning, everyone. We are Team All-Nighters from Typt American School. I'm Jonathan Bruce, the team captain. These are my team members, Alex, Daniel, Rupert, and David.
Yes.
Good morning, everyone. We're from Typt Senior High School, and it's the last day of this competition. The last day of the competition, so enjoy.
Okay. Thank you. So I think okay. Okay. So let's begin this round. So at first, please, opponent challenge.
Team H105 would like to challenge the question number 4, wind speed.
We would like to reject this prompt.
Okay. Reject.
Team H105 would like to challenge the question number 17, helicopter.
We would like to reject.
Okay. Reject.
Team H105 would like to challenge the question number 7, beat dynamics.
We would like to accept.
有试过吗？看动画有试过吗？他们有试看看，试看看。这边呢？放那呢？他那边review。
honorable judges and fellow debaters. I'm the reporter from Beagle High School, and today I'm going to be reporting beat dynamics. So this is the outline of my presentation. First, I'll be introducing this phenomenon and the theory that we have, and our experiments and conclusion. So here's the prompt. A circular hoop rotates about a vertical diameter. A small bead is allowed to roll in a groove on the inside of the hoop. Investigate the relevant parameters affecting the dynamics of the bead. And we will be focusing on the hoop being vertical and that the bead is allowed to roll in a groove inside the hoop. So as we all know, only a body could roll. So that will be mentioned later. So here's a video of our experiment. As we can see that when this hoop starts rotating, the bead goes up to that place. And this is filmed in slow motion. So for our theory, we'll be using the Newtonian mechanics and Lagrangian mechanics. First, we'll be using Newtonian mechanics to analyze this problem. So here we have n cosine theta equals to negative mg. So this is the equilibrium on the y-axis. And for this mass over here, we will only have it will have two forces acting on it. So it's the gravitational force and the normal force. And for the equilibrium on the x-axis, which is horizontal, we'll be using this equation here. So by combining these two, we can have a equilibrium point calculated by r cosine equals to r cosine minus g over r naught omega squared. And here is how we use the Lagrangian mechanics to analyze this problem. So here we consider the friction force being negative BV, and here we have the this is the equation, and the Lagrangian equation considers the kinetic energy and the potential energy. So here is how we consider the rotation kinetic energy and the potential energy when the small bead moves up. And here is the result of us using Lagrangian mechanics to analyze this problem. So we have the equilibrium point, two ways to calculate the equilibrium. So first, when sine theta equals to 0, which means theta equals to 0, this will reach an equilibrium. And number two, when cosine theta equals to negative g over r naught omega squared, which is what I mentioned earlier, it could also reach an equilibrium point. But notice that omega needs to be smaller than, when omega is smaller than the square root of negative g over r naught, the bead will be in stable equilibrium, which means that when the omega is not big enough, then the bead will not move up. So here we fixed our equation a little bit because previously we considered it as a point mass, and as we all know, the prompt says that it needs to roll. So here we consider it as a rigid body, and when this bead roll, it will have this rotation energy. So we think maybe it could affect the equilibrium point. So we put it here into consideration and calculate it with the same Lagrangian mechanics. But notice that the r has changed a little bit because the r naught we have previously is the radius of this hoop, but the RCM we have over here is the radius of the hoop minus the r of the bead. So we calculated using the center of mass of this bead. So here is the equilibrium point we have here. So still, when sine theta equals to 0, it will reach equilibrium. And this r cosine negative g over rcm omega squared is the equilibrium point, and this is the same. So for our experiment, we use an EV3 SQ11 mini camera and a circular hoop. And here is how we control the speed of the hoop. We use a computer to control speed of the servo motor, and here's our vertical rotating hoop. And how we track the height of the speed is using a camera fixed onto the hoop and using a weight to counterbalance this weight of the camera. And to monitor the speed, the rotational speed of the hoop, we use a camera to film the speed readout on the EV3. And here are the different beads we use. We use a metal bead, a marble, and a wooden bead. And here is our results for the equilibrium angle at different angular velocity. And here is the theoretical curve, and here is our data points. But see that here there's a difference, and because this curve haven't been modified to fit the rigid body, and so this is the hoop at 9.5 centimeter, the radius of it, and here is the hoop at 11.5 radius, and this is still the curve is still a fixed curve. So here we have a fixed curve. You can see that it fits better with the data we have over here, and it is because that the radius changed slightly, considering also the bead's radius. And this is the 9.8 centimeter hoop. And here is the data we have for marble. For wooden ball, you can see it all fits pretty good. And for 11.5 cm, it almost fits perfectly. And here we have the equilibrium data for marble, and here for the wooden ball. And so in our experiment, we see that when the bead moves up, it will experience this oscillation, which is the groove mentioned in the prompt. So we want to investigate this, and this is the actual data of our experiment. And we think that this is actually damped oscillation caused by the friction force, which is negative BV, like I mentioned earlier. And this is the theoretical curve calculated by this, and here we can see we have 12, the rotational speed at 12, at 16, at 20, and here is the curve. And here is our actual data, and on top of the curve, a theoretical curve. And so for my conclusion, we can see that our equilibrium angle in our experiment in our theory is that when theta equals to 0 or r cosine negative g over rcm omega squared, the bead will reach equilibrium. And so we consider friction force equals to negative BV, and this causes damped oscillation like we see earlier, the groove. And here, when this is bigger, the damped oscillation period will be smaller. And here are our references, and thank you.
Okay, so first, thank you for the presentation of the report. I would like to ask if it's kinetic friction or static friction?
It's rolling friction.
So if it's rolling friction, is it pure rolling or pure sliding?
It's pure rolling.
So did you consider the width of the hoop?
Our bead can, because our hoop, the inside of our hoop looks like this, so when a bead is in it, it can fit into it.
Fits right into it.
Yes.
So did you consider the material of the hoop?
No, it did not.
Did
Sorry, do you mean,
the
what do you mean by
material
consider?
of your hoop?
We use the same material for all of our experiments.
Okay. So did you think the weight of the bead would affect the experimental result?
No.
Okay. Did you measure the weight of the hoop?
No.
Did you fix the output voltage to stable?
Yes.
So did you think the material of the hoop would affect the result of the experiment?
I think it would affect the friction force, which could be fixed by adjusting the B in the friction force equations.
Did you consider any air resistance underneath the ball?
It's included.
Okay, thank you.
Okay. Only.
It's not working. Can we pause the time? It's not connecting.
显示出来一下，然后这个不见。
So I'm the opponent of team HO105 and I'm going to oppose on question number 7B dynamics. So this is the problem which the reporter just said, and we think that vertical and dynamics are the important parts of the problem statement. Next is the summary, which the reporter just said, and I'll move on. So the points from reporter, there are strong points like using pictures to help with reporting and good observation video, which we can see clearly. And fixed equation by considering real life situation and compare the curve and fix the unfixed curve. But the weak point is it's quite a poor time management because it's too fast, and while using different beat, too many parameters were using at the same time, so you can't really quantify it. Next is I would like to just move on to the discussion. So I would like to ask my first question. Is there any air resistance consideration?
Yes, actually we do. Wait a second. So here we calculated the air resistance and using drag force, and we see that it's very small.
Okay, so, and for my next question is that why didn't the Newton mechanics include friction in that?
Because the results are the same, with or without friction.
Okay. So what do you think about the deviation becomes smaller when the radius is increasing?
The radius of what?
Of the angular velocity, sorry.
Can you repeat the question?
Why do you think about when the angular velocity increase, the deviation becomes smaller?
The deviation of the with the actual data and the theoretical curve.
Yes.
You mean this one?
Yes.
So because this is an ideal curve, and without considering the radius of the bead. So when the bead has a smaller radius, it would fit better with this curve. But when we fix this, it would this curve would change as the bead change as we change the bead.
No, my question is that angular velocity, when angular velocity increase, why the deviation decrease?
Do you mean why it fits better over here?
When your angular velocity increase, why is your deviation decrease?
Okay, so it's because of errors in our experiment. Because when
So if you just said that the errors of your experiment, is there any error percentage?
we can see the error bar here.
Also just error bar.
Yes. So I need to finish the thing I was talking about. So the deviation is smaller because the influence of the error will become smaller when this becomes bigger.
It's not can you switch to the last page on this graph?
The one without fitting.
The one without fitting. Yes. Why when your angular velocity increases, the points are closer to your ideal curve?
Because negative BV has a smaller influence.
Okay. So when you're considering different materials of your bead, the radius are different. So can you quantify it?
Yes, it's already considered it's fixed here using RCM.
So you fix it in your theory but not comparing with your experiment, right?
We did compare it with our experiment.
So, okay. explain the angular velocity increase, but you said that the friction is becoming smaller, so it's closer to the curve, right?
It's influence of the
Yeah,
friction.
influence of the friction, but the velocity is increasing.
Correct.
If your angular velocity is increasing, the last graph without
Here. Okay.
So you said that the friction is not impacting as much as before, right? As the angular velocity is smaller.
Yes.
But when your angular velocity is bigger, your velocity is bigger. So then your friction is bigger. So how can you make sure that the accuracy of your experiment?
I'm talking about the overall influence.
So can you explain the physics explanation bigger?
Because the overall normal force, as we can see here, sorry, here, when angular velocity increases, the whole normal force will increase. So the negative, like the friction force, the influence of it is smaller.
So you mean that when your normal force is increasing, your friction is decreasing?
No, the friction is also increasing the influence of friction.
Okay, so is there any equation you can prove, or did you just think it is an ideal?
Because our main conclusion that we use is over here, and that graph is not fitted for this equation.
Okay, so how do you modify the data?
What data?
Your results.
Okay, so we use tracker to track footage from this camera and to see the angle of it.
So did you know the friction coefficient of the hoop?
We calculate friction using negative BV. Do you mean the B or?
For both feet and hoop.
No, I mean the B, the letter B in our equation. Do you mean that?
Yeah.
Okay, so we have it. Here, we have a coefficient of 0.013, and as we can see in the graph here.
Okay, so I would like to move back to my last question, which you just answered. You measure it by tracker, right?
Yes.
But I'm asking if can you modify it? How did you modify it?
Modify what?
Your data. You just tell me that you measure it with tracker, right?
Yes.
But can you modify it?
Sorry, I couldn't understand your question. Why would I modify?
Okay, so move on to the next question. So in what I just said, the problem statement, I would like to consider dynamics as one of the most important part of the problem statement. So first, did you analyze the B when it's at the bottom of the hoop, when the hoop is accelerating?
Yes.
So you can see.
We have a video.
Yeah, I mean the analyze of when it's
So
accelerating.
So when the bead is at the bottom of the hoop and it starts rotating, it will stay there. So we actually use a little
Okay,
block
so
to
when
increase.
you mean that it stops there, right?
Yes.
So can you tell me where are the dynamics when the bead doesn't move?
So that is why we increase that we move the bead from the bottom a little bit off so that the bead will go up. So there is dynamic.
So I mean, if it's not moving, if you put it right on the bottom, where is the dynamics if it doesn't move it? There's still angular velocity.
Yes.
So I would like to ask, where is the dynamics?
There is no dynamic.
There's no dynamics.
The bead will turn like this at the same point, just like that.
So the bead has a horizontal rotation.
Yes.
So as I just asked you in the short question, is it pure rolling or pure sliding? In my opinion, I think that there's both rolling and sliding. There's partially rolling and partially
In our
sliding.
experiment, we saw that it's pure rolling, and we have a mark on the ball, and we filmed it and see that if it goes up, and we can see the mark goes up with it, and we calculate the distance and how many times the bead roll, and we saw that it's the same. So we think it's pure rolling.
Okay, so consider it as pure rolling while you think there's the rolling fiction, right? Okay, so as I just said, there's a horizontal rotating, right? Did you consider the horizontal rotating will impact the motivation?
You mean the horizontal rotation in the loop?
Of the bead. The bead might be horizontal rotating while it's rolling up, right?
No.
No. It,
No, we did not consider that.
oh, you did not consider that. Okay. So, okay, so can you tell me in a simple answer, what is the impact of different beads? When you're using different beads, what is the main impact on your result?
Okay. So because our equation is already fixed with considering the bead's radius, and we said that mass doesn't really influence this equation. So we think using different bead wouldn't have different results as long as it's not some very extreme situation.
Okay, so for my suggestion to improve this, I think that you might want to consider some parameters the same while changing the others, not changing both materials, radius, and there may be a difference. And there may be mass loss in your rolling, so I think you might want to consider that as a deviation. So, so can you tell me if you move it a little bit from the bottom,
Yes.
what is the main reason that the motion starts?
So the motion starts because it doesn't have enough centripetal force, and it needs more centripetal force, so it moves up.
Okay, so for my last question, I would like to ask, since your motion is like mostly static, so how do you define dynamics and your accuracy of your result?
Here is the dynamics. We have that the bead moves up and down and in this damp oscillation.
Yeah, and the accuracy?
What do you mean by accuracy?
So how accurate do you think your result is?
I think it's pretty accurate.
How do you define it as accurate?
Okay.
Okay, so for my summarize, I would like to say that he considered pretty much parameters, but I think that they could be on different experiments. So they could just change one of the parameters. So we can see the experimental result without using theories and equations to fix it, to make it closer to the curve. And I would like to say that I cannot see the accuracy of his data, so I didn't know if the error percentage is high or low. I didn't know how much time did he did each bead do for experiment. So I would like it to be wrote down in his report, so I could know the accuracy of his report. Thank you.
Well, thank you for both the report and the opponent. The first question I would ask is rather simple. How do you think the radius of the bead and the hoop will affect the phenomenon?
I think because in our equation, as I said again, the radius of the bead wouldn't really affect the whole phenomenon.
It wouldn't?
It wouldn't
be no
affect
change.
us much.
It wouldn't affect as much. What does the opponent believe?
So I think when the angular velocity increase, the resistance of course will increase.
No, I mean if you change the radius of the bead or the radius of the hoop, so you make them larger or smaller, what do you think would happen to this phenomenon?
Oh, the resistance will increase in my
Okay.
opinion.
So what does that mean? How will that affect? Higher resistance means
So the accurate when so you mean when it's in the same mass but just
bigger.
bigger.
Yeah.
The air below the bead will be more, so I think resistance will still.
Thank you. How do you guys think the material of the bead will affect the phenomenon?
I think it will affect the friction force and the coefficient B in the equation.
And would that change your equilibrium angle? Or
No.
no? Okay, what do you believe?
Yeah, I agree with the reporter. There's only friction increase.
Okay. So one thing I want to ask the reporter is, what is the maximum theta you found? So if your velocity went or was close to infinity or decreased in penalty, where do you think the final theta would be?
Do you mean the equilibrium theta?
Yeah, the equilibrium theta.
It will be a little bit smaller than 90, but close to it.
Okay, what do you believe?
Yeah, I think it's close to 92.
Okay. Another thing I would like to ask the reporter is, since you changed the bead material all at once, what did you use for the theory curve? Did you change all the parameters for your theory curve at once? Essentially going back to the theoretical graphs.
Do you mean this one?
Yeah. Did you change all your parameters for your theory curve?
So for this curve, you can see that there is no EV in this.
I'm not only talking about friction, I'm talking about your bead radius as well.
Yes,
So that
but
would
it's
change
in-
your RCM, right?
Yes.
Exactly. So you accounted for that in your theory curve. Okay, so how do you find the different coefficients of friction when you change the material of the bead?
So we have this graph over here, and we can see that it fits pretty good when it's at
Alright,
0.0.
okay. And the last thing I want to ask the two of you is, did you guys consider bifurcation? Whether the equilibrium point is on the right side of the hoop or the left side of the hoop? Did you consider it?
We have given it an initial position.
Okay. The opponent, what do you think? Why does it move to the right or
Okay,
to the left? Thank you. refuting notice of the bead dynamics. So the problem statement is as such. The main focus is that the review believes in is what are the relevant parameters, how can we determine the equilibrium angle, like the critical angular velocity, and how can we explain the oscillatory behavior. So the reporter's performance, they investigated the phenomenon with different angular velocity and how the bead will move to different equilibrium points. And their theory is based on the point mass theory and a rigid body theory as well. For their experimentation, they tested different angular velocities in different types of beads. So the pros of the report is as such. They considered points of mass versus rigid body. They also had clear limits for the angular velocity for their theory. They also examined the oscillatory behavior of the bead. The cons of the report is they lacked a clear phenomenon footage of the bead changing angles, and they didn't test all the relevant parameters, and if they did, they tested the relevant parameters together. They also didn't explain the rate of change in the equilibrium angle, and they didn't account for the slipping on the groove. Another thing they didn't do is they didn't analyze the bead at the bottom of the hoop as the opponent pointed out, and they didn't account for bifurcation. So some of the things about the opponent's performance, they pointed out the changes in the parameters. They also told the reporter to consider air resistance. But however, as the opponent did not consider bifurcation as well, they also could provide an explanation for how changing relevant parameters may affect the phenomenon. They challenged the reporter to the inclusion of friction, but provided no way of including and accounting for that change in friction in the theory. And they also pointed out the possibility of slipping, but they also had no way of determining the slip of the bead. So some discussion topics. The opponent asked, why does the increase in angular velocity mean the decrease in the deviation of the reporter's graph? And the reporter says this is because of errors. The reviewer believes that the reporter should specify what errors it is, and the reviewer believes that this might be because of air resistance, friction, and even slipping of the bead, like the opponent has pointed out. Another discussion topic is how the increase in velocity means increase in friction, and how do you account for that? The reporter says that the influence of friction is decreasing. I'd say the reporter has no justification for this, and the reviewer believes that because F equals negative BV, that means friction is proportional to velocity. So if you have an increase in velocity, you also have an increase in friction, but that doesn't change anything when it's relating to the theory. Another thing is the opponent asked whether pure rolling or whether it was pure rolling or pure sliding friction. The reporter said pure rolling friction. I would have to agree with the opponent that both will impact the phenomenon, and the reporter has no way of justifying that sliding friction is negligible in this case. The last discussion topic I noted is how the opponent asked whether the horizontal rotation of the bead, what would the horizontal rotation of the bead be like while it moves up? The reporter said they did not consider this. I think the reporter definitely needs to examine this, and I think this would relate to the slipping of the bead more than the rotation of the bead. So a few points they have missed is I think the reporter could consider changing parameters one by one instead of changing 3 to 4 parameters at once. They also could include a theoretical explanation for the rate of change in theta for the bead when the hoop is spun at different angular velocities. They also didn't address the slipping of the ball in the hoop and how it might affect the accuracy of their data. And the most important thing here, I think, both the reporter and opponent miss is bifurcation, which is why does the bead move to the right side of the hoop, or why does it move to the left side of its hoop when it's choosing its equilibrium point? And finally, I think that changing the mass, as I was asking it to, would result in a different settling time of the bead for the equilibrium points. And that would be my report. Review. Thank you.
Okay.
So this is my concluding remarks. So we did an experiment on the same bead with different angular velocity, different bead with the same angular velocity, and the same bead with or without an initial position. So that is to address that we didn't control our parameters, but after we did the same bead at different radius of the hoop also. And our theory does not treat the bead as a point mass, but also accounts for the rotational kinetic energy in it. And it would be extremely beneficial if we had included footages of the beads rolling. And bifurcation is neglected because the bead is already given an initial angular position, like I mentioned earlier, because if the bead stays in the middle, the bead won't move up. And here we can see that the bead is in the middle and it actually just stays there and it doesn't go up. So that is why we give it a initial position so that it would move up, and that's why we didn't consider bifurcation in this case. And yes, that's it.
Okay. Some question, review from Joe. Okay.
About the frictional force. No matter you think it's sliding, rolling, or air drag, viscous force, does it affect the equilibrium position of the angle?
No.
I think it would only affect us suddenly at the equilibrium angle, not the equilibrium angle itself. So how long it would take to get to that point?
No, I just the position of the angle.
Oh no.
Okay.
No, that's what.
Okay. And the problem is about dynamics.
Yes.
That means you should study the change of angle with time, right?
Yes.
But if you just look at the final position of the equilibrium angles, that is not the dynamics.
We have considered, we do consider dynamics, as we mentioned, the damp oscillation.
Yes,
there.
I noticed that, but the problem statement actually want you to focus on dynamics.
Yes.
Okay, so that part, you seem to just show the result without any discussion. Now, my question, the last question is, you mentioned in the beginning that equilibrium position is stable. What's your justification?
It's not completely stable, but the
Excuse me, just your justification. Either not stable or stable. What's the justification? Did you anywhere investigate the reasons behind
you mean the reason behind why?
behind stable or unstable?
So we think that it will be unstable at first, and
You
then
think there's no justification. How about you? You think how should it be justified?
The stabilization would be at the equilibrium angle.
Well, just make it simple. Does the angular velocity of the rotation of the pool influence the stability?
Yes, definitely.
yes,
I think there would be.
Yes, definitely. And
So you all know.
I think when when you're focusing on dynamics, it's unstable for me. When it is dynamics, there are too many parameters to be considered.
So you don't investigate the stability problem.
I mean, I would like to defend the reporter in this point about the rate of change in the theta angle. Based on my own experiments and my own investigation of this phenomenon, it's really hard to experimentally track the change when you're spinning the hoop at a really high angular velocity. But yeah, but I think there still could be a theoretical explanation for the rate of change. It's just experimentally it would be extremely difficult.
I think the stability problem is important too. Because if you check the reference, that's one of the highlights of this problem. It has two fixed points, and you have to investigate the stability of the fixed point. One is at the bottom, one is at the top. That's unstable, everybody seems to agree. But then there is one of the vertical axis, and that one doesn't show up until angular velocity is high enough. And when it shows up, is it stable? I think that's important. But from your experiment, you can tell it's stable. If it just stay there, it's stable. But what are the conditions? You don't seem to summarize the regime where it is stable. Well, anyway, other people should ask me. If no other question, I will keep asking.
Okay. Yeah, one or two questions.
I wonder for the reporter, you choose three different material for the heat, and Can you give some reason, motivations for these three specific material properties? And for the other two, I'd like to see your comments about this answer.
We think that this will only influence the B and since B is a coefficient, and we don't think that would make much of a difference to the
So may I
the equilibrium angle.
So, okay.
For me, I think that I agree with the reviewer, which I state in the discussion. I think we should change the parameters one by one.
I agree with the opponent. I think changing the parameters one by one is much more clear in that one of the parameters I think they need to account for is the mass of the B, because I really think that the suddenly tying to the equilibrium point would change drastically.
All right, thank you very much.
Maybe next one question? No? Okay, I have one question. In this page, you say the coefficient of friction is 0.013.
Yes.
How you got that? Because next page, when you match the data and your theory, another page you show your data together with this one.
Yes.
It's obviously that your data seems decay slower. Yeah. So I'm curious how you estimate the B.
So we look at this mainly for the period of the oscillation.
Okay, I see. Okay. So Drew, everyone okay?
This one we know.
Okay, for reporter, the score would be 87777. Okay?
I'm sorry, I have to take it.
You shouldn't announce it.
I think, okay. Let's say again.
Because
Sorry, I'm the first time, sorry.
Yeah, that's okay. We'll take it. Okay.
Can we do this after say 3 minutes, okay? Please.
Okay, so Professor Lin is okay 6. Okay, let me show again. Okay, you're right. Okay, 87777. Okay, and the score for opponent. Professor Lin.
I'm still.
Okay, yeah. Did you okay? Okay, let's rise the score. Okay, score is 545167. And the score for reviewer.
Oh, I'm sorry, I need to correct it because I didn't count the initial one. So actually the reporter is 7, and the opponent is 2. Okay, reporter is 7, opponent is 2.
I think it's okay to change the score. That's correct score. That's 7 and 2. Yeah. Okay.
6.
Okay, let's write the score again.
No, not 9. 6.
For reviewer. Reviewer. Okay, the score is 8, 8, 7, 6, 7, 8. Okay, thank you. Okay, let's have a 10-minute break. Okay, we are now going to Typt and available problems would be here. Okay, so please opponent.
All right, we're going to choose the challenge problem number 2, circling magnets.
Number 2.
Challenge accept. Sorry, Chairman. Can I use the blackboard while I'm reporting?
Yeah, of course. I can use paper.
Actually, can I move your computer over? It seems like I actually see what it is that picture around it. All right, let's just give it a call.
everyone, I am the reporter from Team S603. Today I'm going to explain the phenomenon about the circling magnet. This is our outline today. First, I'm going to introduce the phenomenon first. Next, we'll see a relevant video about the phenomenon. Next, we'll move on to our theory part, and we'll see if the realistic situation matches to our hypothesis and make a comparison with the two situations. Finally, make a discussion and a conclusion about the phenomenon. The phenomenon is that the bottom magnets with different diameters are attached to each end of a cylindrical battery. When placed on an aluminum foil, the object starts to circle. Investigate how the motion depends on relevant parameters. Okay, this is the video of the observation, and due to our experiment, the setup is look like this one, and our document was lost, so I referenced from the internet resource, and it looked like that. Okay. Let's move on to our theory. There are several questions we have to discuss, like the material of the surface and magnetic force of the magnet, and why it will circling, and the meaning of the different rotating radius. Okay, so let's take a look at this graph, and we just analyze the set of Sn and S because the motion of this set will be like this one. It is more easy to observe the phenomenon, and due to this one set will produce unstable sliding, so the root of its motion will be unpredictable. So I just analyzed this motion. So let's move on to our theory. Aluminum is not a ferromagnetic substance but a real electricity conductor. But the copper is a better conductor. The reason we choose the aluminum to be our material of the flatbed is that it is too hard to find a big flat copper and is too expensive. We will start to discuss the reasons that will influence the motivating parameters, like radius of the magnetic or magnetic force and etc. Okay, as you can see, we can calculate the torque of the motivating devices, and we hypothesize that the output of the current of the battery is stable. If we know the circling time and the rotating angle, we can calculate the total magnetic force. And there are also the added current produced by the battery on the left-hand side and the right-hand side of the magnet. Okay. So we can use the norm R1 and R2 to calculate the rotating radius of the left wheel and the right wheel. So the diameter of the magnet is the main reason that decide the rotate radius. Next, I will briefly explain the way we did the experiment. Just set the motivated device on the aluminum foil and then record the relevant parameters. This is our graph of the experiment. As you can see that the velocity of the experimental device is not a level line but a curve. Yeah, like this. And okay, we we do the experiment for 5 times. As you can see, the average of the rotating time is 24.262 seconds, and we can utilize the minimum and the maximum rotating time to calculate the different angular acceleration. And the angular acceleration is between 0.205 to 0.222 radians per second. Okay, so as you can see, the result is not the line, and the result doesn't match our theory. So we discuss every parameter in the device more deeply. We make the comparison to the theory and the realistic situation. We found that the internal resistance of the battery will not remain the same while it is discharging. Below are some definition of the equation we are going to solve next. Q0 means the initial quantity of electricity, and R0 means the initial internal resistance of the battery. R1 means the final internal resistance of the battery. So we can simulate the resistance to a linear changing function. According to the Kirchhoff theory, we can know the second formula. Yeah, and the equation below is just a bit of a standard approach to solve the differential equation. So we can get the integration constant C is equal to 3R1 minus R0 over 2 times Q0. Then we can finally get the relation between quantity of electricity of every moment and time. It is the last formula like this. We measure every parameters of the battery. We need to substitute every constant we mentioned before, and then use the progress to draw the root of the equation. And the pattern is more similar to the realistic situation. It's not just a level line. And we are going to analyze the probable deviation between the experiment and the theory. First is the output current is unstable while the battery is discharging. We just use the linear changing to simulate the realistic situation. The reason is the power of 2 can be ignored in some mathematical similarity. Yeah, and we just use the linear changing to simulate the realistic situation, so it will be not be that precise. And second, the root of the device will not remain the same in every round because the friction is not enough when the speed is too fast. The root will be actually it will rotate like a circle. But the velocity, when the velocity is too fast, it will go out and just not remain a circle. Yeah. And third, there are some original creases on the aluminum foil. It might affect the ability of conducting. The device will short circuit while it is circling. So we are not sure if the conducting heat will implicitize the ability of conducting. Yeah. These are some subsequent expectations. First is finding out the discharging current equation of the battery, so that we can analyze the motivation at every moment more precisely. And second, find how the increasing temperature affect the ability of conducting, because the changing of the heat is unstable. So we didn't take it as a consideration. And last one is try the other parameters like various materials of the flat plate, like different category of the batteries and etc. finally is our conclusion. First, we learn about how the current change while the resistance is linear changing when discarding. And the formula is right below. And we know how the current and the magnetic force cause the device motivation. And we can skip to the short question.
Okay, so I would like to thank the reporter for a wonderful presentation. I just have a couple of questions for you. So you mentioned that heat could be a significant factor in the experiment that you did not consider. Did you happen to measure the temperature of the battery and of the magnets over the course of the
I have measured the temperature because it is unstable between the high heat and low heat. So
Okay.
I did.
Also, did you change out the battery between experiments because you measured that the decreasing voltage and quantity of electricity supplied over the
Because I used the I used the linear change of the resistance, so it is the normal situation.
Okay.
Yeah.
But my question is, you mentioned that you did 5 trials. Did you use a new battery for each trial?
Yeah.
Okay. Also, did you take into account rolling friction in your in the possible source of error or anything?
This is the friction of
I
the,
see.
yeah.
Did you attempt to measure the coefficient of friction that you just
Yeah, yeah, yeah. Sure.
Okay. So what was the value of that you measured?
No, I didn't mention in the report, but this can be easily measured by the simple approach of physics.
Okay.
Yeah.
And also, I'd just like to clarify, so the different parameters that you tested in this experiment was just using one battery and one set of magnets, right?
Actually, different battery, but the experimental result are almost the same.
Okay, but so you use the same type of battery and the same set of magnets for each
Yeah,
experiment?
yeah, yeah.
Okay.
No, not same type of the battery, but same type of the.
Okay, thank you. Jonathan Bruce. I'm the opponent for Team All-Nighters, and I will now be opposing problem number 2, circling magnets. So here is the problem statement again. And my ideal way that I think this problem should be considered is explaining why the circling phenomenon occurs and the underlying principles, as well as potential forces opposing the circling phenomenon, and modeling and observing how the circling behavior changes under different experimental conditions. So now I'd like to go through the pros and cons of the reporter's presentation. I think that the reporter did a good job. He began by considering the aluminum surface characteristics and compared them with those of a copper sheet. He modeled the rotation of the magnets and the forces in play, using Lorentz force of the magnets as a cause of motion, the magnetic force acting on the current. He considered possible sources of error as well, namely the heating of the battery and also the loss of the voltage over time, so the current would not have been constant. And he also had a pretty well-controlled experimental setup. However, I think that there are some things that the reporter could work on here, and I'd like to touch on these in my discussion. First of all, there was little consideration of factors that could potentially oppose the circling motion of the magnet. I think the reporter did a good job of considering the loss of battery voltage over time, but I think he could have also more clearly considered rolling friction, the heating of the battery and the impact on the current as well as energy loss, as well as the presence of eddy currents in the aluminum foil as a result of the magnetic field. I also think that there were some misparameters that could have been tested in his experiments, and yeah, maybe actually this was repeated. Okay, so as I mentioned, the points to be discussed include possible sources of error in his theory and experiments, as well as analysis of different parameters that he could have examined in his experiments. So with that, I believe I'd like to start the discussion now. Okay, so I'd just like to begin by clarifying your analysis of friction.
Yeah.
So you mentioned friction in your theory, but I don't recall seeing any measurement of the coefficient of friction or any inclusion of friction anywhere else in your PowerPoint. So could you just clarify like how much you took friction into account?
You mean the friction coefficient of the magnet or the aluminum foil?
The rolling friction, the friction of the magnet as it rolls on aluminum.
Because we implied the experiment for several times previous. So it will be a root on the aluminum foil so that the rotating of the circling of the magnet and the devices will be the pure rotating.
Okay, but I'm actually asking about that.
Yes.
So did you account for the rolling friction, like the friction as the magnet is rolling and rotating along the aluminum?
You mean the rolling friction will impact the velocity of
Yes.
the Okay. So what I just calculate here is just a rotating friction. Yeah.
Okay, but how did you determine the coefficient of that rolling friction? Because I didn't see it anywhere in your report where you had the coefficient of friction measured.
So that is a simple question. Just put the aluminum foil on the plate and some physics device, and you can measure the coefficient. Right, this one.
Okay, but I believe that is an accurate tool for measuring the coefficient of static friction, perhaps. So in terms of rolling friction, in terms of rolling friction, I think a more accurate way to analyze it would be to sort of have like the sheet of aluminum foil here, and then imagine this is like a top-down view, and then have your magnets here, and then perhaps connected by something that will not produce a current, so it won't produce the any of the magnetic force, and then just set it rolling and analyze the acceleration over time to see how much force is acting on it, because I think we're talking about different types of friction here. So I would recommend this as a method for analyzing the rolling friction. I think that's more suited for static friction.
So how about I compose the several magnets into a big roll, so I can measure the coefficient more accurately.
Oh, so you're saying that in this case you might, using this apparatus, you mean?
This thing is several of the magnets. So
Okay.
it will not produce the magnetic force.
Okay.
Yeah.
But is this like, I guess I'm confused, is this like resting on the surface or is this like actually like rolling?
Rolling.
Oh, okay, okay.
Yeah.
Okay, my mistake, sorry. So I guess that was slightly unclear from the
Yeah.
drawing there. So, do you have a value for the coefficient of friction?
No, I just calculate for the conclusion. Yeah.
Okay, but you did take it into account. Huh?
Yeah.
And do you think that the deformation of the aluminum foil could have an effect on that? Because, for example, if the magnet is pressing into the aluminum foil a bit, it
Yeah.
might sort of increase the friction on the sides there as it's rolling along, if it's pressing in. Because you mentioned that there was some creasing of the aluminum
Yeah.
foil. So do you think that that would also have an effect if it creases the surface a lot?
We are doing do it on purpose because if we didn't have this creases, the magnet, the devices will be too fast and go this way, and we can't analyze the motivation of the device.
Okay, so actually speaking of that, so I think we just discussed rolling friction and came to an understanding on that.
Okay.
How about static friction? Because you mentioned that the device would sort of like leave the circling motion if it went too fast. So did you measure the actual static friction that was between the magnet and the aluminum foil that was keeping it in this circular rotating pattern?
Sorry, no.
Okay. So it sounds like from your experiments, though, you acknowledge that at times the static friction wasn't enough to keep it going in the circular pattern.
Yeah.
Okay, so I think you might want to quantify that and see how you can improve your setup in that way. Yeah, just a suggestion.
Yeah.
And also, so you mentioned heating in your experiment.
Yeah.
So did you, so like approximately, so you say you didn't measure the temperature of the battery?
I said I have measured it, but it goes like the unstable function. So I didn't consider it.
Okay, but do you think that this increase in temperature could have an effect on the resistance?
Yeah.
Okay, so do you think that that could also be a possible cause, in addition to the loss of voltage over time of the magnet, like achieving a constant?
I think
You're slowing down or something.
I think the output of the voltage are still stable, but I think the change of the internal resistance will be changing. But we consider the changing of the resistance is linear to simulate the resistance distribution.
Oh, so that linear assumption was to simulate the heating of the over
Everything.
time. Oh,
Everything.
Okay, I
Yeah,
see.
like yeah.
Okay, and also, how about the energy loss from the system due to heating? Because of course there will be some heat transferred from the battery to the environment. So you think that's a significant factor to consider in addition to the increase in resistance?
So you mean that the heat energy loss will?
Yeah. I'm just asking if you considered that or if you think that's significant in this experiment.
Yes, I think that is significant.
Okay, thank you. And also, I would like to just ask a quick question about your experiment. Did
Okay.
you make sure that the magnet was like completely centered on the?
We drill the magnet on a dot, and after we drill it, we measure the magnetic force of the magnet.
Okay, but when you attach the magnet to the battery, you made sure it was completely
Yeah,
centered,
yeah.
right? Okay. And you also made sure that your table was completely level,
Yeah, yeah.
right? Okay, cool. So now that that's out of the way, I would like to also ask about the parameters. So
Yeah.
you mentioned that you use the same magnets in each,
Different batteries.
but in terms of the magnets stayed the same, right?
Yeah.
Okay, so how do you think that using magnets with a stronger magnetic field would affect your experiment? Do you think that that would be a relevant parameter to consider?
I did change the materials of the magnet because some of the magnet, its chemistry qualification will not let the device go forward or backward. So I choose to fix the magnet to the same one.
Okay.
Yeah. Same material.
Okay, so, but do you think that changing the strength of the magnet would have an effect on the external results?
Yes,
Do you think-
of course.
Okay, so that would be a relevant parameter that you could potentially consider.
Okay.
Okay. And also, how about the moment of inertia? Did you attempt to change the mass of the magnet on each side of the battery?
Because if we change the mass, actually the radius or even the volume of the magnet will change. So the rotating radius will be different. So they are changing two parameters at the same time. I think that is not accurate enough.
Okay, but I mean, I still think like, for example, you could add like a mass to like, for example, this shock. I still think you could add like, for example, a mass that is like non-magnetic to like the outside here and see how it affects the moment of inertia and see whether that's a significant factor in the experiment.
Oh, I have considered this set, but
Okay.
I still think this will resolve the quantity of the electricity will distribute in the over the all devices, not over the this one.
Oh, okay,
Yeah.
okay, I see. I still think that perhaps if you were to use something that's not a conductor, maybe that's an insulator and also doesn't, you could consider that as a parameter.
Yeah.
And another thing I would like to address is also another correction that you could use in your experiment as a force opposing the motion. In addition to heating and rolling friction, did you consider eddy currents that could be present within the aluminum foil?
Because we calculate for the total torque, so we didn't analyze the added current in the magnet. So we just calculate the total.
But how about in the aluminum foil? Did you analyze eddy currents in the aluminum foil? Because I guess what I'm trying to say is assume that like this is your aluminum foil down here. If you have a magnetic field from the magnet going through the aluminum foil, then it could produce an eddy current like this in the aluminum foil that according to Lenz's law would then oppose the magnetic field. So it might actually affect the like actual magnetic force on the battery if there's this opposing magnetic field present within the aluminum.
No, we just mentioned it in the before. We didn't quantify it yet.
Okay, well, I think that would be a relevant sort of correction factor that you could consider for the future. And I think that is all of my questions. Thank you.
Thank you.
Okay, so I think that the reporter and I had a very fruitful discussion. I think we discussed several additional correction factors that he could consider as additional forces in his experiment, namely the eddy currents, as well as the heating of the battery, and we clarified more about his measurements and consideration of rolling friction. And I also suggested that he could consider additional parameters, such as the moment of inertia, as well as the magnetic strength. And yeah, thank you.
Okay. So, fine. So first of all, I want to ask about the air drag. Do you think air drag would affect the whole model?
I think it's certainly a force that's present, but judging by how fast the magnet appeared to be rotating and how much magnetic force there was, I don't think it would be terribly significant.
I just think you mean the air drag?
Yes, the air drag of the when it's moving.
I think it's negligible.
Oh, you think negligible?
Yeah.
Okay. So just one minor issue of yours. You have a angular acceleration.
Yeah.
And I think the unit is incorrect. It's very minor, but just
sorry.
Okay. So you both. Okay. I want to ask about the current in the battery. Do you think that would affect the whole rolling and the force acting on it?
Oh, certainly, because the force causing the motion, as correctly pointed out by the reporter, is the magnetic force acting on that current. So if the current changes, then it would certainly affect the motion.
So do you think that because different types of battery have different structures, so the the electric flow in the battery would be different,
Yeah.
right? So do you think that would make a difference?
Oh, of course, I think considering the voltage and the internal resistance, the battery is very important.
What about you?
Definitely sure. It may affect the angular acceleration.
But you said you used different types of battery.
Yeah.
What types of battery did you use?
Not different material, but the same material but different quantity. Quantity of electricity.
Do you mean the electric current?
Electric current? No. Q. Quantity of electricity.
Okay.
Yeah.
Sure. So for the current in the magnet itself, how do you think the current will be controlled on the board?
So like where is the current inside of the magnet?
Yes.
Okay, well I think that the,
And you too.
okay, I think that the reporter gave an accurate illustration of this. Okay, yeah. Yeah, so I think that just, for example, using this, depending on which direction the current's flowing, it would just flow like this between the, between the battery and the magnet and the coil. So I think that's the way the reporter illustrated it, so I think that's correct.
Okay.
And that is stated forward. And current of this one.
Yeah.
And the side is the attach point. And
Time's up.
the current.
Thank you.
Yes, I would agree with that.
Yes. Thank you.
Okay, so I'm the reviewer and so I'm the reviewer from Legal High School and I'm reviewing circling magnets. So here's the prompt. And here's the reporter's summary. The reporter changed the radius of the magnet and varied the magnetic force of the magnets as two parameters and compared the theoretical model with the actual observed data. And real-life situations such as non-constant discharging of the battery, resistance influenced by temperature increases on the aluminum foil. And their assumptions are that battery discharge is considered to be linear, current is assumed to be linear across all conducting surfaces, and pure rotation and no rolling friction, and the surface is a rigid body. So the strength of the opponent is that they pointed out missed points in the reporter's report, like eddy current, and gave detailed descriptions on how to improve their measurements and observations. And they suggested many parameters that could be important to the experiment. And they utilized the blackboard in presenting his ideas, and he also pointed out the temperature and other things that could be measured and quantified. And here's my question earlier, and I asked them, do they believe that air drag can be influencing the motion? And the reporter think it's negligible, and the opponent think it would influence it slightly. And I think I agree with the opponent more. And I asked them, do you think the structure of the battery can also influence the model? And they both said yes, and I agreed with them. But I think this could be further investigated by using different types of battery, like that has different structures and different flow type inside the battery. And I asked them how the current flow in a magnet, and they both said it's linear through the magnet. But actually, I disagree with them. I believe that it could cause eddy current in the magnet, and I think it should be investigated. And so the opponent's question, and he asked how did the reporter measure and include the rolling friction of the motion, and asked about the maximum static friction. And the reporter said that they assume pure rotation and consider no friction. And we agree with the opponent that the measurement of various frictional forces are important in modeling your theoretical data to fit the actual observed one. So the opponent asked the reporter how do they think magnets of different magnetic force can also be a parameter. And the reporter said that this would definitely influence the force on the whole device. And since magnetic field is one of the central characteristics of the device in your mathematical model, it would be extremely beneficial to include this as a parameter in your experiment. So point miss is the quantification of actual conditions of the system, like the temperature and like the friction force and other things. And suggestions is that the reporter could include their own experimental footage instead of using online sources, and they could include experimental setup and graphs showing how it's measured, and try to measure the battery output and other actual value, and they should dive into what they have mentioned. And the opponent, I think you could mention more about the eddy current and how it influences. Okay, thank you.
Okay, I will start to conclude the presentation, and I want to insert that I do consider the friction of the rotation in the first question what the reviewer mentioned. I just didn't consider the side friction of the motivation, because it will change the direction. Okay, so we will move on the question. Do you consider the static friction which keeps the device stay in a circling while rotating? No, but we consider the kinetic friction between the device and the foil, which we took an average on multi measurements because the foil isn't flat enough. Okay, the question is, did you consider that the heat difference that might cause a difference in the voltage? We considered it in our theory calculation and find it is small enough, but it is too unstable to measure. Yeah. Next question is, did you consider eddy current in the aluminum foil? We did consider eddy current produced by the magnet, or you can take a device in order to make it better correct into our theory, like to quantify it. And we consider multiple reasons of deviation caused to make our theory and conclusion more accurate, which explain most of the opponent's suggestion. We think that we could improve the experiment by adding more parameters and test to it and make sure the comparison between the experimental result and the theory matches with a high or low error percentage.
Any question from George? 这
turn to your theory, the page with your basic model.
Yeah.
Okay, what is the D1?
This is the distance between the rotating center and the mass center of the left wheel, left magnet.
What is the rotation center?
Rotation center is at the circle center.
Okay, do you tie your system with a string with one end fixed in the rotating center?
Sorry?
I do not know why do you calculate the torque with respect to the rotation center.
Because it will cause the motivation of the device. So we calculate the torque of the device to calculate the acceleration, angular acceleration of the devices.
For a system, we calculate torque with respect to a fixed point over the center of mass. But I
Yeah.
don't know what is the meaning of that torque.
The torque means the torque to train heat move forward.
Yeah, they just move. If you have two button magnet of the same radius,
No same radius.
I mean, if you do
Oh,
it,
yeah.
will it rotate?
Yeah, it will rotate, but it will not be the circling magnet. It will go straight.
Go straight.
Yeah.
In that case, how will you torque tau L and tau R? What is the rotating center in this case?
Because this basic model is for the circling magnet, and the straight going magnet is not didn't have its rotating radius.
Okay, another question.
Yeah.
For the opponent, do you see is there any problem in the third equation?
In which equation?
The third.
Oh, okay. I mean, to be honest, are you talking about tau total? Or?
Yeah.
Okay. To be honest, I think that the third equation is correct. It's just adding up the torques on each magnet and then just
Okay.
subtracting out the
And
total.
I
do you?
think after the explanation earlier, I think the torque is incorrect, and I think the torque is acting on the center, looked in the other way. So it's on the center of the magnet. That's where the torque will be.
I would like to say there are two torque and one force.
Oh wait, actually, yeah. Yeah, sorry, I didn't notice that. Yeah, just like to clarify, I would agree with the reviewer that that tau L and tau R should be calculated with respect to the radius of the magnets, and that the friction should be multiplied by R, because that is of course.
I have a comment. I have a comment.
I think another children may have questions.
Sorry.
I wonder, I know probably you already know experimentally mass is not a significant parameters. I mean the battery's mass, but I wonder if what's your opinion about the mass variation of the battery where it is becoming dead?
Sorry, mass what?
The mass of the battery, it's running out of the energy, right?
Yeah.
Can you give us some theoretical or conceptual arguments why the variation of the battery's mass is insignificant?
Insignificant. Okay, so the question is the center of the mass will.
Do you think the battery mass will change?
Oh yes, but we didn't consider it because we even don't know how to make a function of the resistance of electricity. So
Okay, maybe the reviewer or opponents may have some comment. Do you think the mass of the battery will change
I think,
during the experiment?
I don't think it will change.
do you mean in our own
Not at
experiment?
all. Theoretically. Please.
In our own experiment?
Theoretically.
Theoretically?
Yeah.
Okay, so theoretically, if you use, I don't think it will change much, but I think
Why?
it would change a little because the
Yes, why? Please.
because of the distribution of the mass might be different, so the moment of inertia will be different.
I'm not talking about the moment inertia. I'm
Yeah,
talking
and
about
it's, I think it would cause the torque to be a little bit different if the distribution.
No problem. Thank you very much.
Okay, so, yeah, so please vote. Please call. Everyone ready? Okay. So at first, reporter. 3, 5, 6, 6, 6, 5. And the opponent 6, 6, 8, 4, 7, 7. And the reviewer. Oh, okay. Okay, let's multiply. Yeah.
Opponent, right?
Reviewer.
Now reviewer.
The opponent, yeah. Now opponent. Opponent multiply means 6,
So,
8.
So now it is opponent, right?
Okay. Others is the same, right? Okay. Then reviewer. Reviewer. 6, 6, 5, 6, 6, 7. Okay. I think I give very low score to reporter. Yeah, I say the reason because at first it does not show clear phenomenon such as video, it means that, and you do not provide sufficient value of your parameters. And for example, you do not give correct equation, such as this page.
So, sorry, you mean the unclear observation video for the phenomenon?
Yeah, it was video, and for example, this page, your equation is strange.
I know, but I think my.
No, I just explain why I give you a low score. But we can discuss later.
Yeah.
So I also do not really understand your picture of all phenomena. So that's why I give relatively low score. Yeah. So I think if you can have more improve on this part.
Okay.
Also,
so you say the like this picture, or?
Yeah, picture and the equation and the entire model. Yeah, that should be improved.
Thank you.
Yeah. And I also suggest that opponent and the reviewer that you should pay more time to focus on their problem. Yeah, because you provide many possible experiment or conditions they do not do. But in fact, I suggest you pay more attention on what's problem on their already had data, such as this one and the previous. Maybe next one, you have some data function of theta with time. Theta change with time. But that's also a strange result, but yeah, you do not discuss with the reporter, so I think, okay, thank you. And also, yeah, so let's finish this fight, and if sure have a
Well,
suggestion.
there's some time. The question about torque,
Oh, I want to comment before, but,
you know about Faraday's disk?
no, the,
You are assuming,
this is the force, not the torque.
no, the torque formula, it depends on the position on the radius of the magnet. It's not what you just wrote down.
You mean the distance between this one and this one?
Your current is flowing down.
Yeah.
Now, it flows along a radius. At different point of the radius, the velocity is different.
Yeah.
So, the force is different. It depends on the radial distance. So it's not what you just wrote.
So
It should be R squared.
So I make an explanation for, I'm calculating for total current, not the simple point of the current.
No, it's just for a straight wire, you can do that.
Okay, okay.
That's for a rotating disc, it's not.
Yeah, sorry, so we have to break a little bit time. So let's break 15 minutes, okay? We would like to challenge prompt number 9, like this. Number 9.
Problem number 9?
Yeah.
We reject.
Okay. We would like to challenge prompt number 14.
Reject.
We would like to challenge prompt number 12. Your workforce can do it.
Accept.
Okay, number 12.
Rupert from Team All-Nighters, and today I'll be presenting problem number 12, Wilberforce pendulums. So the problem statement says, a Wilberforce pendulum consists of a mass hanging from a vertically oriented helical spring. The mass can both move up and down on the spring and rotate about its vertical axis. Investigate the behavior of such a pendulum and how it depends on relevant parameters. So we believe that the three main focuses of this problem is, one, what causes the rotation and how is it related to the vertical oscillation? Two, how do the natural frequencies of the vertical and rotational motion affect the behavior of the pendulum? And three, what are the relevant parameters that affect the motion of the pendulum? So this is a basic outline of how our presentation will go. We will start with the phenomenon investigation, then the theoretical model, our experimentation and discussion, the comparison of our experiment to our theory, and finally, our conclusion. And so here's a short video of the phenomenon investigation. So as you see, it started off with vertical motion, and then as the mass oscillates, there starts to be less and less vertical motion with a lot of rotational motion. And then fast forward again. There's less rotational motion and more vertical motion again. And so here are two graphs that kind of simulate this motion. You start off with a lot of vertical motion, and as your rotational motion increases, your vertical motion decreases, and then your vertical motion increases again with your rotational motion decreasing. So an intuitive explanation for why the rotation occurs in the first place is because when you pull the spring down, the spring unwinds a little bit, which changes the radius of the spring and gives it a net torque. And as the spring comes back up, it turns the mass and it starts the rotation. And because the energy of the whole system is constant, there has to be some coupling between the vertical oscillation and the rotational oscillation. So before we start on our theoretical model, these are three assumptions that we had. The first is we call the vertical motion z, and so we assume that there's no motion in the xy, or there's no horizontal motion when the spring is oscillating. Our second assumption is that our pendulum has a uniform mass density, and our third assumption is there is no air resistance. So our theory involves a Lagrangian. On the top right corner are our variables and what each variable represents. So the Lagrangian is the kinetic energy minus the potential energy. But notice in our potential energy, we added a coupling term here, a linear coupling term here, to describe the coupling between the vertical motion and the rotational motion. And so the Lagrangian turns out to be that. And then using the Euler-Lagrange equations, I have those two equations. And I can apply those two equations. The first one, I get this second order ordinary differential equation. And simplifying the second Euler-Lagrange equation, I get that second order ordinary differential equation. And so using Python, I could plot the two systems of the system of two second order ordinary differential equations, and I get a graph like that seems to model pretty describe the behavior of our pendulum. And now onto our experimental setup. So in our experimental setup, we have our spring with a cylinder on the outside, which is able to minimize the impact of wind and other motions that could affect the behavior of our pendulum. And the way we recorded the motion of the pendulum is, one, we had a phone directly below our pendulum that's filming, so we can track the rotation later. And we also had a motion sensor to track the vertical motion. And so, how did we analyze the data we collected? As I said, we had a phone that records the rotational motion, and then putting our video files into Tracker, we track the center of our pendulum, and we also track one side of the mass. And we get a vector, and using vectors, we're able to calculate how much angle has changed. And so in our experimental works and parameters, there are 4 main parameters we want to explore. The first one is, the first 2 are the initial conditions. The first ones are the initial conditions, one being the initial height, and the second one being the initial rotation. Other important parameters include the mass and the moment of inertia. And to change that, we can do this. To change the moment of inertia, one way to do that is to change the distance these disks are from the center. And also to change the mass of the pendulum, we can also add different masses on different locations of the mass on the pendulum, which changes both the moment of inertia and the mass. So in our experiment, we will explore the relationship between how the position and the angle changes over time. We will also explore how the period of the motion changes in relation to the initial height and rotation. And we will also explore a critical ratio related to the natural frequency, which I will go over later. So here is a graph of the position of the z motion, the vertical motion of our pendulum in relation to time for 0.5 centimeters. So 0.5 centimeters means that the distance from here to here is 0.5 centimeters. And so this is our experimental graph on top. And as you can see in our theoretical graph here, by fitting the coupling constant, we're able to describe the graph pretty well here. And here is a comparison of our experimental and theoretical graphs of the angle change versus time. So this is the same trial that we had for the previous graph, but this is the angular rotation. And as you can see, the theoretical graph matches, again, pretty well with our experimental graph. However, if you notice here, in our theoretical graph, when the motion goes from its maximum amplitude back to its maximum amplitude, it stays pretty much constant. But in real life, that's not the case because there is damping involved. You can see that the maximum amplitude here is, the initial maximum amplitude is much larger than what we had there. And so to account for this damping, we added 2 damping constants proportional to the velocity, the vertical velocity and the angular velocity, which is denoted by C1 z dot and C2 theta dot. And so after adding the damping, you can see that this is the graph before we had damping where the maximum amplitudes are constant, and here after adding the damping, the maximum amplitude goes down. And so before I explore another important parameter, I would like to define a term that we use in our experiment known as sweetness. So in the vertical oscillations, you can see that it goes between a maximum amplitude and a minimum amplitude, back to a maximum amplitude and a minimum amplitude. And we want to try to quantify how this amplitude changes. And so we find the difference, the distance between the maximum amplitude and the minimum amplitude. We call it the sweetness of the pendulum's behavior. And so what we noticed was that when we change the moment of inertia in our experiments, that distance seems to change. Sometimes there's some point where the vertical motion is able to go to nearly 0 while the rotation is at its maximum. But sometimes the vertical motion doesn't decrease that much. And so we decided to plot, the blue points are the experimental results and the orange points are our theoretical results. We try to quantify this sweetness, and we found out that around 0.000150 moment of inertia, it seems that the sweetness, the distance between the maximum amplitude and the minimum amplitude is nearly the same as the initial pull length we pulled the pendulum down, which means that nearly all of the vertical, the energy in the vertical motion got transferred to the rotational motion. And so we also included percent error of the sweetness we calculated in the graph before. And so what exactly makes that particular moment of inertia so special? What we noticed is that it actually relates to the natural frequencies of the vertical motion and the rotational motion. So the natural frequency of the vertical motion is k over m, root k over m, and the natural frequency of the rotational motion is root torsion constant over the moment of inertia. And we realized that for that specific moment of inertia value that we found, the natural frequency of the vertical motion and the natural frequency of the rotational motion is very, very similar. And that means that the system is resonating, which means that the transfer of energy between the vertical motion and the rotational motion is the smoothest and most efficient. And so, in conclusion, the three main focuses we had, to address the three main focuses in our presentation. One, the rotation is caused by the unwinding and rewinding of the spring as you pull it down and back up, which causes the initial rotation. The second focus is the rotation and vertical motion are linearly coupled, and their peaks are directly opposite of each other because the energy is transferring. And third, the relevant parameters we tested include those. Thank you.
Good morning. So I'm the opponent, and I have a few questions for the reporter. First of all, do you have any graph showing the entire motion for a longer period of time? Because what you showed me, there's only two amplitude changes.
Right. We actually do have for the vertical motion. I didn't put it on my presentation, but for the rotational, because tracking the pendulum's behavior is very slow.
Easier to track.
Yeah, and tracking takes like
okay, so
forever.
please go to page 10. So here you use the Lagrangian mechanics to try to understand the motion of the system. Can you explain why, on the potential energy terms, why is there no gravitational potential energy? Is that intentional or is that a mistake? Because as we all know, as the spring goes up and down, the energy is transferred to gravitational energy, right?
Right.
Can you explain why there is no gravitational energy?
I'm pretty sure the gravitational potential energy is not typically considered in the Lagrange.
Why is it not typically considered?
Because we're trying to describe the whole motion of the system by itself.
Okay, then go to page 9, please. You assume there is no motion on the xy plane.
Right.
Why is there this assumption?
Going back to our video. So the way we actually try to ensure this is, you can notice that there's an
so you try to
axis here,
minimize the
right?
swaying effect,
Right, and so we chose like videos that had the
Oh, so you only
minimum
analyze the best
xy.
videos
Yeah.
footage you have. Okay, so on page 21, there's a damping constant there, but however you say there's no air resistance. I would like to continue that discussion later. Okay, so I'm the opponent, and I would like to first summarize the reporter's report. So he uses a spring with a cylinder in the outside to minimize the XY direction swinging, and he used tracker to track the motion of the motion of the spring, and then he changed the moment of inertia of the pendulum to maximize what he said is sweetness. Next, he started off by saying that there's a net torque when you pull the spring to cause the rotation motion to start, and his assumption is that there's no motion on the XY plane, and he assumed that there's a uniform density of the pendulum and that there's no air resistance. Then he used Lagrange equation to analyze his theory, and then he used an ordinary differential equation solver to actually plot the theoretical graph. And he tried to use the natural frequency to explain what he said is maximizing the sweetness. The parameters he proposed include initial height, initial rotation, mass, and moment of inertia, or disk displacement from the center of the disk. Well, the reporter's conclusion is that sweetness is related to the spring constant, because he mentioned the natural frequency of both the rotation and the translation, right? And another conclusion is that the rotation of the spring is caused by the unwinding of the spring when it is spread out. And the peaks of rotation and translation are directly opposite when the sweetness is maximized and when the moment of inertia is set to a place where the so-called sweetness is the greatest. Now his strengths and weakness is that the report contains the theoretical graph, and there's clear graph explanations on whether the theoretical graph fits the actual observed data. He proposed to investigate many parameters, and he has a great time management skill. However, he did not put the theoretical data on top of the experimental data to show the actual divergence between the two. And I believe that he considered damping proportional to the velocity of the spring mass. However, he just assumed that there's no air resistance. So I would like to ask him about that later. Then he did not give me a clear answer on whether gravitational potential energy is neglected or whether it is intentional in his formula. And he didn't show how each parameter actually influences the result of the experimental outcome. For example, the period of the wave, or for example, how the rotation and the translation interact with each other. So here are the points to be discussed. First, I would like to talk about the air drag and damping. Then I would like to ask him about the swinging of the pendulum. Then I would like to ask him about different parameters that he proposed, and then finally why there is a linear coupling between these two values. I would like to start my discussion now. So as I just mentioned minutes ago, please go to page 21. So there's a damping constant here that you try to use to figure your radical curve to your experimental data, right? Please turn to the page, the previous page. The previous one. Okay, so as you can see here, there seems to be a divergence between the theoretical data and the actual data. So why do you think there is this difference?
Well, because our previous theoretical did not account for it.
Okay. So this is the energy loss or the amplitude loss is because of damping, right?
Right.
Then what is the reason for that damping effect?
Well, damping has a variety of causes. One could be like when the spring is moving, there's some type of friction between some type of sound loss. And also, actually, I do admit that there is air resistance. What I meant by no air resistance was previously when we set up the Lagrangian, we didn't have damping in it.
Oh, so then you try to.
Then we try to account for that.
So you actually account for it. So. Okay, so next I would like to talk about on page 10. You have this term, right? So I asked you about the gravitational potential energy previously. Do you have a new answer for that? Are you neglecting gravitational potential energy intentionally?
I believe by literature it's quite common that the Lagrangian does not include the potential energy.
So others research didn't include the.
Right.
Okay, so then I'm really confused by this term, because you propose that there's a linear coupling between the v direction and the rotational motion of the mass, right? So why is this way? Why is it coupled like that?
Oh, because the energy of the whole system is pretty much constant, and there has to be energy transfer of energy between the vertical and the rotational.
But why does it couple linearly?
It couples linearly because if you look at if you look at the energy, this term here and that term here, the relationship between is proportional when the energy is transferred. And also, if you think about it from a logical standpoint, when you're moving, the spring is moving back up, then the spring is not, like, it's rewinding back up, and that's.
Okay, so this also fits your experimental data, right?
Correct.
So is this your assumption at first, and then you check out your experimental data and prove that this is correct?
Correct.
Okay, then I would like to continue our discussion to page 19. Again, it is this graph, and you just mentioned there's damping effect, right?
Right.
Then I'm really curious whether the swinging of the spring really doesn't influence your experimental results. Because you said that you try to minimize the swinging, right?
Right.
But how did you do that? And by minimize, what do you mean?
Okay, so I do recognize that swinging will cause our experimental data to be inaccurate, but as I said from this video, we hand selected the best experimental results that we had, and the way we try to minimize how much swinging there is we try to find experimental our trials that where the vertical motion of the pendulum basically aligns with the tripod behind.
Okay, so can you turn to the page where you show the rotational motion and the graph of the rotational motion and the vertical motion.
Is it this one you're looking for?
No, that's good. I wanted to ask you whether you have your a graph where you layer the rotational motion and the translational motion on top of each other, so that we can see clearly what you mean by sweetness and how the energy is transferred.
Oh. I didn't actually overlay the graphs together, but if you notice that the scale is actually the same. So the maximum here is around 50, and the minimum here is also around 50.
Okay,
For
so
the same
these
trial.
two graphs are from the same trial.
Or from the same trial.
Okay, so so you said that you try to maximize the sweetness, right? And so you try to change the moment of inertia of your disk. So how did you do that? Like, how does the moment of inertia actually influence the energy transfer?
So to clarify, you asked me how I changed my moment of inertia in my experiment.
Yeah, because you said that you try to maximize your
Right.
sweetness. Right?
So this is like a screw. You can turn it in and out to change the distance.
Okay, so how exactly does the moment of inertia influence your experimental results? So far, you've shown me the maximized moment of inertia.
Right.
But
So we tried various moment of inertias, and these were the sweetnesses that we found.
okay.
And we found out that there was one particular moment of inertia that gave a very high.
But do you have the position versus time graph and the angular position versus time graph where the different sweetnesses occur? Do you have the graph for different sweetnesses, or do you only analyze the greatest sweetness that you find?
Well, I analyzed the sweetness of each. I analyzed the sweetness of each position versus time graph, and I found the value of that sweetness, and I plotted that sweetness in relation to the moment of
But
inertia.
I would like to see whether how sweetness actually influenced the entire graph. Do you have that?
I don't have a graph for that, but I can tell you what happens.
Okay, so for the so-called wrong moment of inertia, the energy transfer is not that obvious. Is that correct?
Correct.
Okay, so you show us only this.
Right.
Okay, so I would suggest that if you are to, for instance, on page 9, you said that you neglect the XY plane motion. So I would suggest that if you are to really neglect that motion, you will have to put experimental footages to show us that that motion actually doesn't influence the experimental
Well, from
outcome.
the data that we collected, that we already minimized it such that there's basically no observable XY motion
Okay.
in our video.
Then I would like to go to page 10. So, why is there 1/2 here? Is that,
Okay, well, this is a coupling constant, so it doesn't really matter what kind of
so
constant.
you just
constant
put
is
it
here.
there to make the whole equation?
Yeah, you can change the constant to
okay.
whatever fits your experimental results.
Okay, I would like to end the discussion.
Thank you.
Okay, so first of all, I asked about the reporter's assumption that there's no air resistance, but he replied to me that it is because that is only assumption for this particular equation. So he actually changed that, and I later asked him about the sweetness, what he called sweetness, and I asked him about the moment of how the moment of inertia actually influence the graph influence the motion of the mass. However, he said that he does not have the graph for that, and he does not have graph to show us how the energy actually transfers from one type of motion to the other type of motion.
So firstly, I would like to ask about, okay, so for your equation of the Lagrangian, can you translate please? It says that's the mass. It says that's the mass, but it doesn't really exactly tell us about what the mass of the node that is on the below, or the mass that includes the mass of the spring. And do you think the mass of the spring would affect the whole system?
It only includes the mass of it doesn't include the spring. The spring is a lot lighter than the mass. So,
Oh, okay,
yeah.
so you think it can be like that. Then do you think that the mass of the spring
I
will
believe
change?
that the mass of the spring is neglected in that obviously.
Then what if the spring is, it has a lot of mass, then how do you think it would change the results?
Well, I believe that in his experiment he actually used a spring with the mass not that large, so it doesn't influence the equation as much.
Okay, I see. Then I want to ask, how do both of you think the motion on the xy point? I know you have already assumed that there's no, but however, if there is, then how do you think that will affect the result?
Well, the amplitudes will certainly decrease because not all of the energy is either in the vertical motion or the rotational motion.
Yeah, I see.
I would say that there will be more discrepancy between his observed data and the theoretical data because the energy is transferred to the xy plane motion instead of the potential energy that he proposed.
So then both of you have discussed on the air resistance that would change the damping to the vertical movement, right? Then can you please turn to the graph which includes only the graph where it's rotational movement? Yeah, so for right here, you only have like you only see one curve. Then how do you think the air resistance, because when you spin like that, you certainly also have the air resistance going this way. Then how do you think will that change the rotational motion if in the same way with the?
Of course, because damping decreases the overall energy in the whole system, and so the available energy to transfer to rotational and back to vertical decreases as well.
So only changing the amplitude, right?
Yes.
Okay, then what?
I believe that damping actually only changes the amplitude, but there might be some energy loss to the system, so the equation might need to be modified.
Okay. Then one more question. For that one, can you please explain, like briefly explain why do you think there is like it's slightly different between the theoretical and
Well,
experimental?
the general pattern is there. I believe what happens is when we were tracking, there might have been some small errors. But because the general pattern is there, we know that data is going to be accurate.
Okay, that would be my only question. Thank you. not only gave a very clear explanation of their theory, though according to the further discussion, we think that we both sides agree that there would be more corrections to be made. And then they also gave a comparison of their theoretical and experimental data, which fits very well, and even after the correction, it fits even better. And then for okay, so and then for their conclusion, they think that most of their parameters changes mostly changes the result of their data. And then points from reporters, something that they did really good was that they also after their experiment, they considered many different corrections to be made, and then they also have a really good simulation of how the theoretical thing would go. And then, but they sometimes I feel like they haven't given enough physical explanation behind these equations. For example, why they used the Lagrangian, what conditions, under what conditions can the equation can be used, and they didn't mention how the percentage error is calculated. For example, I think I see one of the error percentage was like 23%, and I'm not sure why that is so big. And they also have lack of an environmental deviation correction, though I do realize that they had it to like maybe prevent their spring from moving. And then points from opponent, he cleared many things that we were confused about their report, and then they though his time management was not fully fulfilled, but he did still ask many main points, and then but some detailed questions. For example, the question I asked about why is there a slightly difference between the experimental and the theoretical thing on the page around 19 was some detailed question that has been missed. And also, so the main part of the main clash was that the mass. So what I think. So from what I asked them because they didn't mention that if the mass they assumed was included in the spring or not, but I certainly do agree with them that if they think it should be if they think there's a big difference, then it can be neglected. But I also think that the mass of the spring can be a parameter to be investigated in the future. And then they also, I also asked them about the resistant rotational movement. So we do agree with them that they have, we do agree with the opponent that we should make a correction in the equation. And then they also talked about this, the moment of inertia. And then I think the reporter gave a really clear explanation of how they got the inertia, but it would be better if they just, it would be better if they I think it would be better if they clearly shows that in the report. And then they also discussed the cost of the coupling constant relationship, coupling constant, which I think if we're not, I think that most equations, most researchers says that, and it is a assumption that we just made. So I think that's perfectly fine for the thing that they asked, and that will be it. Thank you.
So these are my concluding remarks. First, to address the issue of the XY motion, we handpicked all of our footage to make sure that there's minimal XY motion. So we didn't have to include that in any of our theoretical models. Second, air resistance is definitely a factor, and that's why we included the damping factor. But we also believe that it only affects the amplitude of the whole motion. Third, the spring we used had relatively small mass in relation to the mass that was attached to the spring, so we neglected the mass of the spring. Four, we didn't overlay the graphs because we believe that it would be too confusing to have too much on the same graph. But if you look carefully, the scales on the axes are actually the same, so you can compare the two side by side. And fifth, we use the Lagrangian because the whole behavior of the pendulum is about a transfer of energy, and that's what the Lagrangian describes. Some improvements that we do acknowledge that we can improve on. first is a graph that overlays the rotational and the vertical motion to show the transfer of energy between vertical and rotational motion. But again, the axis scales are indeed the same, so if you put the graphs side by side, you can still see the transfer of energy and the maximum and minimum peaks in relation to each other. And lastly, another improvement that we could make was the reviewer pointed out that on my rotational graph where I tracked the data, there was some smalls, although the general pattern is still there. So we will use better cameras and do better tracking for that. Thank you.
Any question from Joe?
My question is always, why you use Lagrangian formalism instead of Newtonian mechanics?
Because we think
Because Newtonian mechanics doesn't work, or what's the problem with Newton's formalism?
because I think that
It's harder.
the Lagrangian best describes the energy.
No, I disagree. I always say Newtonian formalism is better because it provides you detailed formulas for your coupling constant, everything. If you analyze the bending moments, you should use Newtonian mechanics, not Lagrangian. And that's one drawback of your whole presentation, that those parameters has no theoretical basis. You don't connect it to any property of the spring or the elongation, the strangeness or the torsion. You don't have that connection, right? If it's in Newtonian mechanics, you will definitely have it. Isn't it correct?
Yes.
So how about you? You're against the Newtonian mechanics?
I think if both equations suits both kind of equations suits the motion, then I think it's better for us to compare those.
My question is short. Is that a drawback of his formalism?
Yeah, I think maybe he could use both, and that would be better.
Well, I would like to defend the reporter here because if he were to analyze the motion of the spring at each point, although he can really understand the coupling constant and
No. This has been done maybe 100 years ago, so the analysis is not that difficult. It's not a point by point. No, it's not like that. Okay, my question.
Any other question? So the
No
situation
question.
can be discussed later.
I would like to ask the reporter, can you say it in more explicitly that why didn't you include the gravitational term in your Lagrangian?
Because the Lagrangian I set up was solely the behavior of the pendulum system itself, and we didn't consider the external.
Why? Why you didn't consider it? But it's there.
Yes, it's there.
well, I believe the gravitational energy is actually already accounted in his formula because the Lagrange equation uses partial differential equation. So when you so it can be fit into the spring potential energy, and when you do the math, it actually cancels out. So the gravitational potential energy doesn't have to be inside that because when you do the differential equation, it actually cancels out to zero.
Let me put it another way. If you don't complicate the situation, you just think of a simple spring hanging there, and then you have weight. It will have a different position of equilibrium position, right? Now, if you start from the equilibrium position with weight, and then you consider small amplitude vibration or up down, you don't need the gravitational force, because it's a vibration about an equilibrium point, which is determined by the spring constant only. And I think that's what's the theory used. But then you have to be careful that it's a small amplitude. But in your experiment, I saw you didn't mention this. How long is the spring, and then how much displacements are involved? If it's small, you don't need to consider gravitational force,
In
right?
our case, it was relatively small, but we only put
Okay,
like
good.
7
That's good.
centimeters. Yeah.
Okay, I have a short question for opponent and viewer. Okay. The reporter do not consider the mass of spring. So how do you think the contribution of the mass? What is the contribution of that? And the first question. And the second is, in their case, they consider linear coupling between the angle and the distance. Like they have Covington theta z, for example. Should you agree that? Please answer.
Well, I agree with the assumption of linear coupling because at first you don't know how it actually couples. So as the reporter says, he first assumes a linear coupling, and after the actual observation, he found that the linear coupling actually fits his data.
Yeah, I do agree with the coupling thing too, because he just said that it's just his assumption. That means it's what he put before he did the experiment, and if the coupling didn't match the linear part, then he certainly would adjust it. But because it fits, so he thinks that it's right, and I think that's.
And what's the mass from spring?
Well, I believe that the mass of the spring would account for the difference in his equation. But however, as the reporter says, the mass of the spring is really small and negligible. And I would suggest that if you were to say that, you would have to include the calculation of the mass.
So I think if the mass is big enough, then it would certainly affect the distribution of the mass in the whole system, and then that will have to take into account to where exactly all the energy has gone, like have it all gone to maybe the.
So what's the ratio of the spring mass contribute to the system? Do you know that?
I'm not sure.
Okay, let's see that. So, all yours, with your okay, first the reporter. Okay. 7, 8, 8, 7, 8, 7. Okay? And the score of opponent. 7, 7, 6, 3, 7, 7. And the score of reviewer. 8, 7, 5, 2, 7, 8. I think the score of from Professor Lin is quite low relatively. So
Yes, I can make a comment both for the opponent and the reviewer. They ask the detail of the subject or the experiment. And but all these are not relatively quite connected to the problem. They didn't see that actually reporter give a relatively good report and focus on the essence of this physics problem, which is that you have two systems. One is a rotational one is an oscillational one. And usually we already learn this, right? That we already learn that separately the rotational one and the linear oscillational one. But the interesting thing is that when these two couple together, what happened? And actually, the reporter showed a very interesting phenomenon, which is the resonance. And you can realize and understand the energy translation, why you get the maxima or the 100% translation when the oscillation, when the resonance happens. And this is actually a general feature of the many phenomena around the world. And because many in the real situation, that many systems actually couple and exchange energy. And this is one very interesting way to at least qualitatively understand this. Now both the, and for this part, the reporter actually addressed on this point. But the opponent and the reviewer really didn't see the significance of this essential characteristic of the problem. So I think they both miss the main point and ask some. Well, for example, that from in the whole morning, the question of the air resistance has always been raised. But I think in all three questions, all three subjects, the problem, the air resistance, air friction, is kind of secondary. Not really play an essential role on all these three problems. But I really do not understand why I constantly heard this question raised. Before you ask question, you should first judge that if this point is, when we get the air friction in all these three problems, yes, we all get the air friction acting on all these three problems. But are they essentially in any of it? I think it is something that you have to evaluate before you ask this question. You ask relevant question, not the question there, but maybe only very minor effect. That's my standard to judge the opponent and the reviewer, which is that not just ask a question, but ask relevant question. And I think I hold the consistent criteria for the all three ways.
So,
Could I give a comment? Please read books which use Newtonian formulas. Okay? Then you know all the coefficient in terms of your displacement or the coupling term. For example, you Sommerfeld, which is both German physicists whose students, many of them Nobel Prize, but he himself didn't get it because lack of innovation. But he's good in physics. Sommerfeld, very clear how these two motions are coupled. You have to study the property of the material. Actually, the most important one is shear modulus. You didn't mention any thing about that. These coefficients has to do with shear modulus or rigidity, and of course including Young's modulus. Okay, nobody ever mentioned least important property of materials in this respect. That's why you didn't get 9 or 10. Okay. Otherwise, the report I think is excellent. It's
so I think we can have more suggestions in this round. So let's thanks all Jules and all teams' contribution. Okay, thank you.
Thank you.